I got a request for number 11 in chapter 3, and it's asking us to calculate the net electric charge of a peptide. And you're asked to do this at a couple of different pHs, 3, 8, and 11. So this is a monster problem. It's basically 3 problems in one, giving you a lot of practice on how to calculate electric charge at different pHs. The concept here is you look at the pH that you're interested in and you compare it to each pKa on the peptide. And I should say, of the peptide's ionizable groups. This is really similar to calculating the overall charge of an amino acid. You calculate the charge on each ionizable group, and then you just add them all together. So the first thing you do is you take a look at the peptide and you identify which groups we're going to be analyzing, which groups are ionizable, which groups are titratable. So you look at a pKa table, and in this problem you're told to go ahead and use table 3-1 out of the book. On an exam, you'll be given a pKa table on the front page. So the first group, starting from the N-terminus, that we'd look at is the amino terminal end of the first amino acid. So that'll be an amino group there that we care about. We also know that glutamic acid has an R group that's ionizable. We also know that histidine has an R group that's ionizable. Tryptophan, serine, glycine, leucine, they do not. So we just skip on over them. Arginine has an R group that's ionizable that we're concerned about. Proline doesn't. And then it's going to be the C-terminal end, which is the carboxyl group alpha glycine, that we're going to take note of. And so here it might be useful to make note of what the ionization states are. So glutamic acid, when it's protonated, it looks like this. When it's deprotonated, it looks like this, has a negative charge. Histidine, the R group is neutral when it's deprotonated, and when it's protonated, it's got a positive charge. That goes for the same with arginine. Neutral deprotonated, positive charge protonated. And over here we've got our C-terminal end. I did forget to look at the N-terminal end as well. So those are all our groups. In the solutions manual, you can see that they made a chart, which is really helpful. So we can go and recreate that chart for ourselves, or that table. So I wrote out all our ionizable groups, and above each I put the pKa value. So let's look at what each group is going to look like if the pH is 3. And so we know that when the pH equals the pKa, you've got 50-50 of each of the forms, protonated, deprotonated. When the pH is greater than the pKa, you're going to have more deprotonated form. So I'm going to put A- because we know we're familiar with that terminology. It's the conjugate base. If the pH is less than the pKa, those acidic groups haven't gotten deprotonated yet. So you'll have more of the HA species rather than the conjugate base. One thing to note is you could do Henderson-Hasselbalch to get the amounts of conjugate base and acid, but there are some rules that you can remember to avoid having to do that extra math. If you're 2 or more units away, and that's, I'm talking comparing the pH with the pKa. Then you're going to be 99% one form and 1% the other form, basically all protonated or all deprotonated. And which one it is depends on if you're above or below the pKa. I think one issue that students had with this problem is that in class we calculated things more precisely. In this problem, they rounded everything to whole numbers. And so when do you have to do the rounding and when do you have to be more precise? It depends on what you're being asked. So if you're asked to calculate the overall charge to a precise number 1 or 2 places past the decimal point, then you're going to have to do some Henderson-Hasselbalch equations. In this problem, they're doing a lot of rounding up, so we'll go ahead and do that, and that's because the question doesn't ask you to report the answer with much precision. So if we're hanging out at a pH of 3, what's this first group going to look like? That amino group on the N-terminus, its pKa is 9.67. All the way down at pH 3, this group is going to be all protonated. It is not going to have lost its protons, so overall charge of +1. There's no partial species, there's no partial charges associated with this group. So we go over here to glutamate, and so just to remind ourselves, the protonated version is neutral, the deprotonated version is negatively charged, and so at a 4.25 pKa, if you're at a pH 3, without doing Henderson-Hasselbalch, I know that you're going to be mostly protonated. So you're welcome to do Henderson-Hasselbalch for this problem, but one thing that I remembered is that 1 pH unit away from pKa, you're going to be 91% one version and 9% the other. And so at 4.25, that's a little bit more than 1 unit away, so it's going to be even more than 91%. So I'm going to put a little about 91%. It's going to be approximately a little over 91% protonated, because we're below its pKa. And so if you're going to calculate that into a charge, it's going to be neutral. So you're going to have over 91% being neutral. So since we're rounding to whole numbers, the charge contribution from the R group of glutamate is going to be 0. It's going to be very little deprotonated groups. And so if you wanted to get particular with the numbers, you can do Henderson-Hasselbalch and figure that out, but it's going to be less than 0.09 negative. And so that's going to be small enough that this problem finds it negligible because it's rounding to whole numbers. Now moving on to the R group of histidine, it's pKa 6.0 at pH 3. That R group is going to be all protonated, and so you need to have your knowledge of the structure down so that you know the protonated form is going to be positively charged and everything's going to be protonated, so that's a +1. For arginine, same thing there. We're at a way lower pH than its pKa, so all of that will also be protonated. We go to the carboxyl group at the end, and the pH is a little over 1 difference. So let's look at this. We got CO- or COH are our options. The pH here is greater than the pKa of this group, and so you're going to have mostly deprotonation. So you could go ahead and do Henderson-Hasselbalch for this problem if you wanted to have precision. But again, I know that there's going to be a 91% to 9% difference when we're 1 unit away, and we're even more than 1 unit away. And that makes me feel confident that we're going to be a little over 91% deprotonated. So let's say if you were going to write that out, the deprotonated form is negative, so that would be like a negative 0.9 something. I'm not doing the Henderson-Hasselbalch, so I'm not exactly sure what the number is, but since they're rounding the whole numbers, that easily rounds up to a -1, no matter what number is past that 9-digit. So now that we have the charge contribution for each of those groups, we just go ahead and add everything up. So +1, +1, +1, -1, so that's 3 minus 1, which would give us a +2 net charge on this peptide. So doing the same process for pH 8 and pH 11 is going to be exactly the same. So I think again, I'll say I think the hang up for this problem for students was that there wasn't any Henderson-Hasselbalch done, which is the more precise way, but you're not being asked for partial charges in a very precise way, so you're able to round up. That said, if you did Henderson-Hasselbalch, you'd get the same answer too. So feel free to do that as well for those groups that are a little bit closer than 2 units away.